Climate change is not only reshaping our landscapes, but also the lives of the Arctic's top predators. As the Arctic climate warms, the once distinct boundaries between polar and grizzly bear habitats are blurring. With grizzlies venturing northwards and polar bears confined by diminishing sea ice and food, their paths are crossing with increased frequency. The close genetic relationship between these two species allows interbreeding. As their habitats increasingly overlap due to environmental changes, it has gave rise to hybrid bears, commonly referred to as Pizzly and Grolar bears. A Pizzly bear specifically denotes a hybrid whose lineage includes a polar bear father and a grizzly bear mother. Conversely, a Grolar bear is the result of a grizzly bear father mating with a polar bear mother.
The Arctic climate is extremely important to look at due to the Arctic amplification effect, which refers to the rate of warming taking place in the Arctic. The Arctic warms at twice the global rate, meaning that slight temperature change globally will have greater consequences for the Arctic region. To understand current climate change taking place in the Arctic, it is important to look at temperature and precipitation occurring throughout the Holocene, which refers to the last 11,700 years. Going back to the early Holocene, the Arctic experienced a warming period as a result of declining ice sheets, which lowered the albedo, causing more warming to take place. Albedo is how much of the sun's radiation is either reflected or absorbed by the Earth, depending on the surface type, with ice having a high albedo due to the white surface reflecting a large amount of solar radiation, whilst dark material, such as soil, has a lower albedo. In the middle to late Holocene period, there was a decrease in the summer solar radiation, causing a cooling in the Arctic. This is likely a result of both volcanic activity and, most importantly, the Milankovitch cycles, which is a slight variation in the Earth's orbit or tilt, which influences how much solar radiation the Earth is receiving over a long period of time. There was a 3.5 degrees Celsius cooling which occurred in the late Holocene period, which resulted in the Little Ice Age taking place in the 1600s, which also aligns with the orbital changes due to the Milankovitch cycle. The last 200 years have seen a shift from this cooling, with temperatures increasing by 1.5 degrees since the Little Ice Age, likely a result of human influence. There are large amounts of data to support this, which highlights that 4 out of 5 of the warmest decades in the last 2,000 years have occurred between 1950 and 2000, with the Arctic being the most affected by this warming.
There are many proxies used to help understand how temperature has fluctuated throughout the Holocene in the Arctic. One being the use of oxygen-18 isotopes from shell-forming organisms called foraminifera. Proxies are preserved characteristics of the climate in many different forms used to help reconstruct the past. Oxygen can come in 3 different isotopes, 16, 17, and 18, with the ratio of 18 to 16 allowing temperature at the time of the shell formation to be discovered. The amount of oxygen-18 is higher when there is declining temperature and hence an increase in ice volume. In addition to this method, there is also the use of tree rings, with the width of the ring indicating the temperature at time of formation. This is only a short-term proxy as the data does not extend far back in time, but does allow high resolution for the Arctic climate in more recent years. Leading from this, the northern tree line position fluctuates depending on climate conditions, so this could be a good indicator for long-term climate variations. In the first half of the Holocene, the tree line was at the northernmost position because of melting glaciers allowing for migration north, which reinforces a warming period at this time. In the last 3,500 years, the tree line has remained relatively stable despite the cooling which has occurred, showing that this proxy has a broader timescale than others. Though there is evidence that over the last 100 years, despite the tree line staying stable, the density of the forest has increased as a result of recent warming post the Little Ice Age. All methods combined offer crucial insights into the significant warming trend in the Arctic over the past 200 years, linked to the Industrial Revolution. This trend has led to a marked reduction in sea ice, with a 9% loss per decade, exacerbated by albedo changes. Understanding these changes is essential for comprehending the evolving Arctic ecosystem, crucial for understanding the distribution and adaptation of grizzly and polar bears, and how it influences the emergence of hybrid bears.
Different bear species have different traits. Grizzly bears live in North America, adapted to forest and mountainous terrains with an omnivorous diet. They also adapt to what food sources are available, eating food like fish, large mammals, berries, nuts, and insects, depending on the season and specific region. This is in contrast with the predominantly carnivorous diet of polar bears, who specialize in hunting marine mammals like seals, who are confined to living on the Arctic sea ice. As the climate continues to change, the availability of critical resources like food becomes increasingly uncertain. This is particularly evident in the case of polar bears, whose reliance on sea ice for hunting seals highlights the delicate balance within their ecosystem. This delicate balance is further exemplified by the polar bear's specialized diet and unique hunting grounds.
The polar bear's diet is made up of approximately 80% seal young of that year. These seals are dependent on sea ice to survive. Therefore, if sea ice declines, this vital food source will also decline. As a result, polar bears are forced into fasting in ice-free months earlier in the year, and they will have fewer fat reserves. Polar bears fast for 4 months of the year. This time is increasing with increasing temperatures. This impacts polar bear cubs' health, and as a result, polar bears adapt to the changing climate by migrating further north to areas with greater amounts of sea ice, especially in areas with greater seasonal ice variation. In areas with higher rates of sea ice melting, such as in Hudson Bay region, polar bears' populations are more affected by climate change and have a greater northward migration. Therefore, polar bears' habitat is being reduced with the increasing annual temperatures.
Concurrently, as the climate warms, there is a noticeable northward shift in vegetation zones, which is facilitating the northward expansion of grizzly bear territories. Grizzly bears, being ecological generalists, are able to adapt to a wide range of food sources, which makes them more resilient to changes in their environment compared to more specialized species like the polar bear. This adaptability allows grizzlies to expand their niche northwards, following the shift in vegetation and prey species. This encroachment into traditionally polar bear-dominated areas are leading to increased interactions between the two bear species. This convergence of territories, marked by transitional zones between ecosystems, is where hybridization between these species occurs. In regions like the northern Canadian archipelago and parts of Alaska, melting sea ice and changing ecosystems are driving these species to coexist in the same habitats. Notably, areas around the Beaufort Seacoast and Victoria Island have become hotspots for observing Pizzly and Grolar bears, indicating these areas are active zones for hybridization. Pizzly and Grolar bears exhibit a unique blend of characteristics inherited from their parent species. As a result, these hybrids display dietary versatility, incorporating both terrestrial and marine food sources. Importantly, these hybrid bears have also demonstrated the ability to breed, indicating that they can contribute to genetic exchanges between polar and grizzly bear populations. Looking at the population size, there is an estimated total of 32,500 grizzly bears and 26,000 polar bears in the world today. However, accurately quantifying the population of hybrids poses challenges due to their rarity. The increasing number of documented cases, as reported by Polar Bears International in 2021, indicates that the emergence of these hybrids is anticipated to accelerate with the progression of global warming.
Also, hybridization has played a significant role in the evolutionary advantages of various species, offering insights into how gene flow between species can lead to adaptation and, in some cases, the emergence of new species. In the natural world, hybrids can arise between closely related species, leading to introgression, where genes from one species become integrated into the gene pool of another. This process can introduce new traits and behaviors that may be beneficial for the parent species. The interbreeding between modern humans and Neanderthals is a notable example, with most non-African humans today possessing some Neanderthal DNA. This genetic exchange has been linked to several adaptive traits such as immunity to specific pathogens. In the animal kingdom, hybridization has also led to significant evolutionary outcomes. For example, bison in North America have interbred with domestic cattle, leading to beneficial hybrid traits in some populations. Darwin's finches in the Galapagos Islands have experienced hybridization, which has contributed to a rapid evolution into new species due to changes in environmental conditions or habitats. Understanding the nature of hybrids, particularly in the context of climate change, is important for several reasons. The hybrids between polar and grizzly bears can exhibit traits from both species, potentially offering them adaptive advantages in changing Arctic environments. This combination could make them more resilient to the challenges posed by a warming Arctic. The adaptive potential of such hybrids may make them more adaptable and flexible to varied diets or habitats, demonstrating the role of hybridization in species survival under shifting climatic conditions. However, hybridization also poses a risk to pure local species like the polar bear, which is already under threat due to climate change. The gene pool of polar bears is relatively small, and the prevalence of hybrids could lead to genetic swamping, where the distinctive genetic traits of polar bears may be diluted by the more dominant gene pool of grizzly bears. This could hasten the decline of polar bears as a distinct species, and the outcome could be a loss of the unique adaptations that polar bears have for their icy habitats, further endangering their survival.
So, what will happen in the future? What lies ahead for polar and grizzly bears amidst climate change remains uncertain, especially concerning the emerging hybrid species like Pizzly and Grolar bears. What's clear, however, is the urgency to address climate change to protect these bears and their dwindling habitats. These hybrids highlight nature's adaptability and the mounting pressures from climate change. With ongoing habitat overlap, hybridization is likely to increase, potentially reshaping the evolutionary paths of these iconic species. Addressing climate change is crucial for preserving the unique Arctic ecosystem and ensuring the survival of its native species.